This is a gate problem on random variables and correlation. X is uniformly distributed between -1 and 1. N follows a normal distribution with zero mean and unit variance. X and N are independent of each other. We define y equals x plus n and z equals x squared plus n. We need to find the correlation between x and y and the correlation between x and z. Key insight: in signals and communications, the correlation between two random variables x and y means E of x times y, the expected product. Since x and n both have zero mean, this equals their covariance. And because x and n are independent, E of x times n equals E of x times E of n, which is 0. This independence condition will kill all cross terms. Computing the correlation of x and y, E of x times y equals E of x times the quantity x plus n. Expanding, E of x squared plus E of x times n. For x uniform between -1 and 1, the second moment E of x squared equals 1 over 3. You can verify. Integrate x squared from -1 to +1, divide by 2. The cross term E of x times n equals 0 by independence. Therefore, correlation of x and y equals 1 over 3. Computing the correlation of x and z, E of x times z equals E of x times the quantity x squared plus n. Expanding, E of x cubed plus E of x times n. Now, x cubed is an odd function, and x is symmetric about 0. So the integral of an odd function over a symmetric interval is exactly 0. All odd moments of x vanish. The cross term E of x times n is again 0 by independence. Therefore, correlation of x and z equals 0. Correlation of x and y is 1 over 3. Correlation of x and z is 0. The answer is option A. Two key takeaways. First, odd moments of any distribution symmetric about 0 are always 0. Second, independence kills all cross terms immediately.